What is information? Imagine you are observing a coin flip. How would you quantify the amount of information you get from each observation? This is exactly the question that is addressed in information theory. By the end of this video, you will understand the important concepts of information and entropy. This will help you with the more advanced topics that we often encounter in machine learning or deep learning, such as the Kullback-Leibler divergence or the evidence lower bound. Let's head right into the concept of information. We consider discrete random variables for now, which means that there are a limited number of outcomes of the random event. Examples would be a coin toss or a roll of a die. The amount of information gained in the observation of a random variable is directly related to its probability. Let us now think about a function that can map a probability to an information value. For example, if you for some reason knew the outcome of the coin flip already for all future tosses, there would be no point in still observing it, as there is no information to be gained. On the other hand, if you buy a lottery ticket and are not sure about the outcome, the information gain in the scenario where you would win would be very high, as the outcome was very unlikely. Thus, for the information function, we want something that gives us large values for probabilities close to 0 and very small numbers for probabilities close to 1. Additionally, think about the information gain from the observation of two separate random variables that are independent from each other. It makes sense that the overall information is simply the sum of the individual information values. In terms of probabilities, for two independent random variables, this is simply the product of the probabilities. So, let's recap our requirements for the information function. It should map probabilities from 0 to 1 to an information, while having additive behavior for independent probabilities. Basically, the logarithm function is a perfect choice for this. It is strictly monotonically increasing, which means that for increasing values of x, also the value on the y-axis increases. Additionally, it fulfills our requirements for the multiplication, since it allows to split up the multiplication into an addition. What is missing now is that lower probabilities should result in a higher information than those with a higher probability. We can simply flip the logarithm by multiplication with -1 and have found our information function. Outcomes of a random variable with a low probability give us high information value, while the information for those close to 1 becomes 0. You might have noticed that the base of the chosen logarithm is 2. This is for historic reasons, since originally the concept of information was introduced for communication signals where bit streams consisting of zeros and ones were transmitted. Now that we have a quantity that describes how much information is present in one single observation of a random variable, wouldn't it be also nice to extend this concept and quantify the information content of the whole random variable? Entropy, how Shannon introduced it, is exactly that. The average information for the whole random variable. Using the expectation operator, we can compute this average weighted with the probabilities of the single events. Remember, the expectation is computed as the sum of the function we want to evaluate, multiplied with the probability over all values of the random variable. We now insert our information function and evaluate this expectation. This gives us the Shannon entropy. The square brackets here denote that we are dealing with discrete random variables. This term is named after Claude Shannon, who laid the mathematical foundations for information theory and also introduced the word bit while working on communication signals consisting of zeros and ones. It is said that Neumann suggested the word entropy not only because of the similarity to the concept in physics, but also because nobody knows what entropy really is, so in any discussion you will always have an advantage. Let's take a look at two examples. Here we have a communication signal consisting of 3 bits with equal probability. We can have 8 different combinations of the bits to be transmitted and thus assign a probability of 1/8 to each of them. We want to know how large the entropy of this signal is, which is now our discrete random variable. For this, we directly insert into the formula of the entropy. I will go over the calculations shortly, but make sure that you pause and try to solve it on your own before. Since all probabilities are the same, we can simply insert 1 over 8 for them. Then we split up the logarithm and the 1 vanishes as the logarithm of 1 is 0. Now we have a term in the sum which is summed over 8 times. So this corresponds to a multiplication with 8. The result is 3 bits, which makes sense as we have a sequence consisting of 3 bits. In the next example, we will take a look at a setting where the symbols do not have equal probabilities. Again, try to compute the example and see what happens. This time, we need to write down the entropy sum explicitly. The result are 2 bits, which is lower than previously. The distribution of the states seems to be linked to the entropy of the random variables, meaning that there might be a maximum or a minimum of entropy that we can achieve. We will take a look at that in the next parts. To find out about the extreme cases, where entropy is either minimized or maximized, we will take a look at what happens when we take the probabilities to the extreme. When one probability is 1, so the event is always occurring, the entropy of this random variable is 0. On the other hand, it is possible to show that the uniform distribution, as we had it for the coin, the die, or the first communication example, is the distribution which maximizes the entropy. The entropy then becomes the logarithm of m, where m is the number of states in the distribution. Up until now, we considered a finite number of states and discrete random variables, but what will happen when we go to continuous random variables with an infinite number of states? Will it still be possible to assign information and entropy quantities as we have seen them? We again start with a discrete random distribution. Now we let the number of states m go to infinity and see what happens. Previously, we saw that for a uniformly distributed discrete random variable, the entropy could be computed as the logarithm of m. But when m approaches infinity, the entropy would also be infinitely large. Shannon introduced the concept by simply exchanging the sum with an integral. This is now called the differential entropy. However, he did not derive the formula, but rather assumed it was the correct form. Note that we also exchanged the square brackets with the round ones to show that we are dealing with continuous probability densities now. Today, we know that the continuous and the discrete entropy are only conceptually the same, but differ mathematically. This does not limit its applications though, as we are going to see. For example, we can again find a distribution which maximizes the entropy, similar to before when we found out that the discrete uniform distribution maxes the Shannon entropy. It is possible to derive that the Gaussian distribution maximizes the differential entropy. There also exists a closed form for the entropy in this case, dependent on the variance sigma squared of the distribution. Let's see what happens when we increase the variance, or in other words, what happens when the distribution becomes wider. You notice that the entropy increases with higher values of the variance and can also approach infinity. This was not possible in the discrete case. Now, we make the variance smaller. The entropy can also become negative in this case, which again, in the discrete case was not possible. The minimum of the Shannon entropy was 0. Think back to the beginning where we considered the requirements for the information function. One of the requirements was that for 2 independent random events, the information should be additive. But what happens when the events are not independent from each other? This is where conditional entropy comes into play. It quantifies how much information is still left to observe in an event that follows another one. Look at this setting, for example. We have a coin where the result of the toss depends on the current weather. If it is currently sunny, the coin will always land on heads, and thus the conditional entropy is 0, since the outcome is already determined by the sunny weather. On the other hand, when it rains, the coin is unbiased and the entropy is still 1. To show how we can derive this, we assume that an event X has happened. Then, the probability of y afterwards is p of y given x. We can directly insert this probability in our definition of the entropy by considering the joint probability for x and y. This time, however, we need to integrate over both variables. The result is the conditional entropy. Of course, there is also the discrete version of the conditional entropy, which again looks the same, just with summations instead of integrals. Finally, before we summarize our findings about information and entropy, we need to take a look at two important properties of the conditional entropy. For this, we use Bayes' theorem to rewrite the conditional probability. This we can insert into our definition of the conditional entropy and get the sum of two integrals, since the quotient in the logarithm can be split up. We see that the definition of the entropy appears twice here. First, we have the entropy of the joint probability. In the second term, the variable y will be marginalized out, and the result is the entropy of x. By rearranging the three parts of this sum, we can see that we arrive at our initial condition for the information. If variables x and y are independent, the entropy of both together is simply the sum of the individual entropies. Also, it is not possible to increase the entropy of a random variable by observing another variable. This is written down in this inequality here, which means that the maximal entropy for y is obtained if no previous knowledge is available, or if it does not depend on x. If y depends on x, any available observation for x only decreases the obtainable information gain afterwards. In this video, we discussed the fundamental concepts of information and entropy, beginning with how information is quantified and leading up to Shannon entropy, differential entropy, and conditional entropy. Understanding these principles is crucial for more advanced topics in machine learning and data science, such as the Kullback-Leibler divergence and the evidence lower bound. If you are interested in such topics, check out my playlist on the fundamentals of machine learning, where I explain the mathematical fundamentals that are necessary to understand it at a deeper level.